Welcome to Math 361, Statistical Methods 1. This is the first online video lecture. We'll be covering the first part of Chapter 3 in the textbook. Our topic will be the measures of center and variation for a data set. First, we'll talk about measures of center, then we'll talk about measures of variation, and in the middle, we'll talk about how to calculate these quantities using our graphing calculators. So first, a measure of center quantifies the center or middle of a data set. Consider the following sample distributions. The blue distribution appears left of the red distribution, in the sense that the center or middle of the blue distribution lies to the left of the middle or center of the red distribution, at least when we're talking about the horizontal axis. So a measure of center will quantify where along that horizontal axis does the middle of a data set fall. Three commonly used measures of center are the mean, median, and mode. Most students have encountered these before and may remember them as the three M's, since they all begin with the letter M. We'll talk about these in order. First, most importantly, is the arithmetic mean, or simply the mean, of a set of data, and that's the measure of center found by adding the data values and dividing the total by the number of data values. In other words, it's taking an average, using our everyday language. However, in statistics, we'll call this finding a mean. Now, depending upon where the data comes from, we have different formulas, at least in terms of symbols, for representing a population mean on the left versus a sample mean on the right there. Now, the population mean is denoted by the Greek letter mu, at least a lowercase mu. And in the numerator, we see that we have an uppercase sigma. That means a sum in mathematics. This says sum up all the x values, where x is our general variable just to denote our data values. So sum up all the data values is what that's saying in the numerator. Occasionally, we'll see more precise notation where it says sigma k equals 1 to n of x sub k. So that says sum up all the data values starting with a subscript of 1 going up to a subscript of n. K is the index of summation, 1 is the lower limit, n is the upper limit. That's usually saved for calculus and other more advanced courses, and I think we may only encounter that a few times in the course. Your textbook usually just uses sigma without any superscripts or subscripts, and it'll just say sigma x, sum up all the x values. Now we divide that by uppercase n, that's the population size. Now compare that with the sample mean formula on the right. To denote a sample mean, we use x bar. We still sum up all the data values in the numerator, except for these data values come from our sample, not from the entire population. And now we divide by lowercase n instead. This is the sample size. In both cases, you're doing the same thing, summing up values, dividing by the total number of values. Make sure throughout this course that you use the correct notation for the problem at hand. If you are dealing with population values, use mu and uppercase n. If you're dealing with sample values, which happens most of the time, we'll use x bar and lowercase n. The median of a data set is the measure of center that is the middle value when the original data values are arranged in order of increasing or decreasing magnitude. Important part here is the arranged in order. I don't just want to spread out my data values and just pick the middle one. I want to make sure they're ordered first in order to figure out what is the middle value of my data set. Now, when there's an odd number of data values, it's pretty easy to do. We just pick the middle value. But when there's an even number of values, say 6, what we'll do is we'll take the mean of the middle two values. So we'll take the third and fourth value and find the mean of those two and report that as the median of our data set. Finally, the mode of a data set is the value that occurs with the greatest frequency. Quite often, this is not really useful for quantitative data. However, it's the only measure of center that works with categorical data. So often, if I'm looking at a data set of people's favorite color, I would report the mode as my measure of center there. It would make no sense to calculate a mean favorite color. Round-off rules for the mean and median, we usually carry one more decimal place than is present in the original set of values. So if my original data values are integers like age, my mean age I would report would go out to 1 decimal place, maybe 17.4 or something like that. And it doesn't have to be even a value that's in my data set for the mean and median. Like, those are often values that I don't find in the data set itself. However, the mode, since it's the value that occurs most often, is going to be a number that is present in your data set already, and so therefore we report that value without performing any rounding whatsoever. Now let's look at an example. Considering the following data set, 12, 23, 5, 17, 12. Find the mean, median, and mode of this data set. Pause the video now, and then, using the formulas in the previous slides, calculate these three quantities, and then come back and check that your answers match mine. So we'll look at the sample mean, since I did not specify which type of mean to calculate there. You get the same number, we just use different notation. So I'll say x bar is the sum of x over lowercase n. So that means I need to sum up 12 plus 23 plus 5 plus 17 plus 12 in a numerator and divide that sum by 5. The resulting value is 13.8. 13.8 what? Well, it'll depend on the units in the original data set. Now to find the median, I'll first have to order my data set. That's in the upper right-hand corner. I see there that there's 5 values in odd number, so the middle value is easy to pick out. The median is 12. And also the mode is 12 as well. Now I don't have good symbols for denoting the median and mode, so I'll just use the words median and mode to denote those two quantities. I hope your values or your answers matched my own here. Now we'll move on to the graphing calculator to show you how to enter the data and calculate these same quantities, which hopefully will match up with our answers. So now we'll look how to calculate these measures of center using our graphing calculator. First, we need to get our data set into the calculator. So as we saw in the first lecture, we'll go to the Stat menu and hit Edit. Now, I don't want to erase my data set from lecture 1, so I'll go out and enter this example problem into list 2. So my data values are 12, 23, 5, 17, and 12. So once I have the data entered, remember that it's list L2 now. I'm going to second and hit mode to quit, go back to the main screen. So now what I want to do is I want to calculate some quantities. I go to Stat, and I arrow over. I'm not going to do the edit. My data is already in there. I'm going to go to Calculations. And I want the first option, 1 var stats, because I have one variable here. So I hit enter, and it says, oh, 1 var stats. What list do I want to use? I want list L2. So to get the list names, I need second stat to go up to the list menu. So second stat, option 2 is list L2. Hit enter there. So list L2 is involved. Frequency list, well, it's just raw data, so I don't have a frequency list. Leave that blank, and then I go down to calculate. Now I hit enter. So what I'm looking for here is either the mean, median, or mode. So first off, the first quantity here is x bar. The calculator assumes this is sample data. So x bar is 13.8. That matches with what we got in our hand calculations. Now if I arrow down, I get minimum value of x, and here is MED, that's the median value, is 12. That matches with what we got. Now mode is not listed here, so we're on our own for that one, right? But the mean and median can easily be calculated using this 1 var stats function on your graphing calculator. Now we'll talk about measures of variation. A measure of variation quantifies how spread out the values in a data set are. Consider the following two example distributions. The blue distribution has a wide range of values at a pretty high frequency, whereas the red distribution has most of its values somewhere around what I would consider the middle of that distribution. While it does cover a wide range, values far away from that middle section occur with a very low frequency. So I want to find some measures that can quantify this spread of data. Three commonly used measures of variation are the range, the variance, and the standard deviation. A fourth measure, the interquartile range, or the IQR, will be discussed in class. So first, the range of a set of data values is the difference between the maximum data value and the minimum data value. Important here to note it's max minus min, so that means we need to sort our data set, just like when finding the median of a data set. You don't just want to take the last value and subtract from that the first value. This should be a non-negative result. Second is the variance. The variance of a set of data values is a measure of how much data values deviate away from the mean of the data. So how far are they away from the middle of the data set? Once again, depending upon where the data comes from, we have different formula for dealing with population variances versus sample variances. The formulas are almost identical, just like in the comparison of population mean to sample mean, but the sample variance formula on the right has a different denominator. So on the left, we'll start with the population variance. It's denoted by sigma squared, that's the lowercase Greek letter sigma. It's equal to, now in the numerator, we have a sum of squared deviations away from the population mean. That's an x value. We take a data value, subtract from that the population mean, that's its deviation from the mean. Now square that result, do that for all the data values and sum them up. Now why a squared deviation? Well, if we just summed up deviations, then some positive deviations and negative deviations would cancel out. We don't want to do that. So we square them instead. So this way we have all non-negative squared deviations that we're adding up. In the end, we're then going to take that final sum and divide by the total population size, uppercase N. Now, one nice feature of this is if a data value falls very close to the population mean, then its deviation is fairly small. Imagine it's really small, like 0.1 or 1/10. Then when I square that, 1/10 squared becomes 1/100th. So a value very close to the mean contributes very little to this sigma squared quantity. Whereas a value x that was very far away from the population mean would have a very large deviation, say 10, and then when I square that, 10 squared becomes 100. And so therefore, values far away from the mean contribute a lot to the sigma squared quantity. So in an entire data set, if all the values are near the mean, they're all going to contribute very little to this quantity, and I should get a fairly low value of sigma squared. However, if all the data values are very far away from the mean, so it's very spread out, then I'm going to have a lot of large deviations, and so that numerator will be fairly large, and therefore sigma squared will be fairly large. So it seems like in terms of measuring the spread of a distribution, variance does a good job of doing that. Now on the right we have the sample variance. We switch from sigma squared to s squared for the sample variance. In a numerator we once again have a sum of squared deviations, but this time they're from the sample mean. Mu is replaced by x bar because I'm assuming my data comes from a sample. Now in the denominator, this is our big change. It's not lowercase n, it's lowercase n minus 1. We'll talk more about why that is in class and later in the course, but for now, just think about this. Sigma squared, the population variance, is a parameter of the population. It exists, but I never know what it is. So what I would like to do is take a sample, calculate some statistic, well, it will give me a good guess at what the true population variance is. So the statistic I'm going to do is s squared. I want that to be a good guess at sigma squared. Well, it turns out if you divide by lowercase n, your s squared won't end up being a very good guess for sigma squared most often. So instead, we have to divide by n minus 1. This ensures that our guesses are better. What n minus 1 does mathematically is it decreases the denominator, so it makes a smaller bottom of that fraction, so that the remaining or the resulting quotient when we do the division will be larger. So n minus 1 actually inflates the values of s squared from if we just had n down there. So since we'll most likely or most often be working with sample data, the thing to remember is we most often want to divide by n minus 1. Now if you look in your textbook, there is a quote shortcut formula for calculating s squared, and it involves doing some algebra in the numerator there, expanding out all those x minus x bar squares, but don't ever use that formula. Don't bother trying to memorize it. Once we get enough data values where you'd want to take a shortcut, we'd probably just move the technology and use the technology to calculate S squared for us instead. So remember this formula. That's a good one to have, but don't bother with the shortcut formula in the textbook. Finally, the standard deviation of a set of data is the square root of its variance. Now, that means the formulas are pretty easy to remember. If you remember the formulas for population variance or population or sample variance, you then have the formulas for population standard deviation and sample standard deviation. The reason we have two different measures of variation that are so closely related is twofold. One comes from mathematics, that some theorems or formulas require variance and some require standard deviation. So this just gives us two different symbols to use, so that's helpful. And another one is in terms of the units of the data. If we go back to the variance formulas, if x is measuring age in years, then sigma squared is going to be in the units of years squared, or squared years, because the x minus mu will be in years, and then I'm squaring that, and that's where the squared years come from. But I don't know what squared years is really representing. That seems like a weird unit. I have a hard time interpreting that. So, nice thing about standard deviation is when I square root a quantity that's measured in squared years, that would mean that the standard deviation would simply be back in years again. So standard deviation is in the units of our original data set. So that's a nice feature of working with standard deviations. So back to our example data set. This time we want to find the range, sample variance, and sample standard deviation of this data set. Pause the video here and calculate these quantities by hand using the provided formulas. Hopefully at the end your solutions will match mine. So first, to find the range, we have to order our data set in the upper right-hand corner. We see that the max value is 23, the min value is 5, so 23 minus 5 is 18. I have no notation for the range, so I just call it the range. And it's 18 what? Well, it'd be whatever units the original data set are in. Next, to calculate the sample variance, I have 1/4, so that is the divide by n minus 1. There's 5 data values, so I divide by 4 instead here. So I just pull that out front. And now in the large parentheses, I have a sum of squared deviations. So I take each data value, subtract from that the sample mean, which is found previously to be 13.8, and I take that result and square it. And I do that for each of the 5 data values, and those resulting squared deviations I sum up then. And when I divide by 4 in the end, I get 44.7. That's an exact value. Once again, rounding rules. If it was 44.72, I would round it to 44.7 here, 1 decimal place further than the original data set. Finally, to calculate the sample standard deviation S, I simply take the square root of the previous S squared quantity, square root of 44.7, rounded is 6.7. Do note that if S squared were really 44.72, when I calculate S, I would want to take the square root of the non-rounded sample variance, meaning I would take the square root of 44.72, not the square root of 44.7. Once you start rounding in the intermediate steps of these calculations, you're going to introduce more and more rounding errors, and in the end, your rounded answer will actually be incorrect, even though you follow the correct procedure for calculating it. So remember, try to keep all your values as precise as possible until the very last step, and that very last step will be your rounding then. So hopefully these values matched up with what you calculated by hand. Now let's move back to the technology, look at our graphing calculators, and determine how to calculate standard deviation and variance using the calculators. Returning to the graphing calculator, now we're going to go calculate variance and standard deviation. Once again, we'll need to have our data in the calculator, so it should still be there, but just to check, I'll go and hit second stat to get the list variables, and I'll see what's in L2, 12, 23, 5, 17, and 12, so that's our data from earlier. So to calculate variance and standard deviation, I once again use the one_var stat function. So I go to stat, go over to calc, one_var stats, hit enter. And now my list once again is L2, frequency list is still blank, and I go down to calculate. So there's my X bar, 13.8. But I see further down here I have SX. That is 6.7. I also get sigma x, which is 5.98, or if I round it correctly, it's 6.0. So I do get the population standard deviation as well as the sample standard deviation. I do not get variances, however. So if I wanted to get the variance, what I would need to do would be to type this into my calculator, say 6.68580586, and then square it, and that would give me my sample variance. The final quantity range is not spelled out for us, but it does give me the maximum value, 23, and the minimum value, 5. And so I could subtract 5 from 23 to get 18 there, which matches with the range we calculated by hand. So in summary, a measure of center helps us quantify the center or middle of a data set. 3 common measures of center are the mean, median, and mode of a data set, the 3 M's. Also, a measure of variation quantifies how spread out the values in a data set are. 3 common measures of variation are the range, variance, and standard deviation of a data set. A 4th measure of variation, the interquartile range, or IQR, will be discussed in class. Make sure you understand how to interpret these quantities, what symbols are used for these quantities, and what the formulas look like. Thanks, and I'll see you all in class.